we finished discussing introducing sets and functions. I think it's pretty elementary. We didn't talk about the very kind of special cases. It's all the thing you have to know, even for you to become an educated user of optimization. Now let's finally move to the definition of optimization problems. Okay, there's many different ways we can introduce or define optimization problems. Let me stick with I think a little bit special structure, but general enough. All right. Suppose we consider a general nonlinear optimization problem. It's just where x is a decision variable, where it is in Rn. Okay, we want to find x, and also x has a domain D, which is not. You can say that here belong to D. It's fine. We want to find x which minimize this particular function. F is called a cost function, right? Cost function, which is F0 maps from Rn to R. The cost function, it has to be mapping vectors or some kind of decision variables to the scalar. Okay, we don't consider vector valued function optimization, which is multi-objective optimization. We don't consider that. So it only maps decision variable to a real scalar, which indicate how good or bad certain things are, right? And at this part, and we want to find x, but this x has to satisfy this particular constraint, right? There's two types of constraints. One is called inequality constraint. The other one is called equality constraint. All right, so there's only two types of constraints. Sometimes people don't really explicitly consider equality because equality can be handled by less than or equal to 0 and bigger or equal to 0. So, but in general, we can write this way. Okay, and the value, the x satisfy this constraint are called feasible. Okay, so for example, I will define a set. Let's call it set C, which is x belong to Rn or belong to D. Let's say x in Rn, such that if I of x less than or equal to 0, hi of x equal to 0. This is I from 1 to m. This is I from 1 to q. Okay, so this is called a constraint set. So we want to find the optimal value, optimal function. Suppose this is my f0, and I also need to specify I want to only look for optimal solutions within this set. Okay, that will be my constraint set. All right, and x belong to this is called feasible, primal feasible. Like this. Okay, if f belong to this constraint set, then x is called feasible. All right. This problem, if I write this way, it's a standard optimization, nonlinear optimization. It could be convex, could be non-convex, could be linear, could be nonlinear. But it's all satisfied this general structure property. Okay. So a particular class of optimization problem that I think it's very important is called a convex optimization problem. Roughly speaking, it means all these f's are convex and h are affine. That's a little bit specific kind of a definition, but in general, convex optimization means the objective function f0 is convex. That's important, and the constraint set is also convex. The function is convex, constraint is convex, which gives us the convex optimization problems. If we minimize a convex over a convex constraint set, that's an convex optimization problem. And because of the special structure we listed here that requires all these functions, f0 all the way to fm need to be a convex function, then the constraint set will be convex. And also this the equality constraint, we only allow them to be a affine function. That's a that can guarantee this. Okay, this condition can guarantee the constraint set is convex, right? Why convexity is so important? Because convex optimization can be solved very efficiently. Let me dive a little bit more into the categories of optimization problems. Let's say categories. How to say categories, right? So there are two things defines a optimization problem, if you're roughly speaking. So it's objective function and also constraint set. These two things determines the complete optimization problem. Okay. Let's say if the objective function is linear, or let's say affine, and constraint set is also all linear. I'll say constraint set or function. Okay, the set is defined in terms of level set of function. So if the constraint functions f, for example, is linear or affine, this gives us the problem, which is a linear program. Okay, and if the objective function is not linear anymore, it's a quadratic. And also constraint set is linear and affine. That's what we mean by quadratic program. Okay, that's what I mean, or most people refer to QP or quadratic program. That really means that this, right? But of course, there are there's some kind of ambiguity in terms of this terminology. You could also say this is a quadratic, then constraint set is also quadratic. Okay, we know also, sorry, this is a quadratic program. Well, we know quadratic functions may not be convex, right? So when we say QP, typically we mean or refer implicitly means the cost function is convex. Okay, let's say that. Let's mention some kind of convention or implicit. Okay, so this is convex. And in general, if that's also have a quadratic constraint, this is called QC-QP. Okay, this is called a quadratic constraint. And QP quadratic program. Most of the time, this part may not be convex. All right, so that gives us pretty hard problems. Since in general, this can be very hard. Okay, this can be hard to solve. Okay, so the cost maybe is still convex. Let's assume that. Okay, if the cost is not convex, it is another story. And if you have a quadratic constraint, if the quadratic constraint is also not convex, then the problem is quite hard to solve. But some people you can still call it quadratic program for some text or other literature. But when we use robotics, when they say formulate a quadratic QP problem, oftentimes we mean really kind of a nice convex problem with linear constraint only. Okay. And also, if it's not quadratic or it's not affine, it's only, we can say it's convex, And also this convex condition will be convex program. Okay, that's just two special cases I want to list or discuss in detail. With that, we can draw a little bit figure about, let's say this is my ILP linear program. Okay, this is a QP. Okay, that's the very special case, right? And then I can say a little bigger than that. This is a QP. And this QP, what we mean by QP is really convex QP with a finite linear constraint. That's a little bit harder to solve than ILP, but almost the same, but it's more general. Okay, and there's another important class which is called, maybe we won't be able to discuss them in detail. It's called it's not QCQP, it's a second order Cone program. Okay, the constraint set is a cone, it's a second order cone. We introduced the set of cone, the cone particular set that are can be defined as cone. So this one is a little bit, it's also a convex problem. Let's draw another figure. This is then we another one is semi-definite program, semi-definite program called SDP, semi-definite program, and this is a special convex optimization problem that we're going to introduce in the next lecture, lecture 12. Right? That's quite important class of convex optimization problem for control especially. And then we say, if it is not SDP, then we say whether it's convex or not, that contains that. And then later on, okay, the figure grows to the right. This is a general nonlinear optimization problem. Okay, you need to recognize different categories of these optimization problems. Everything inside, let's see, hold on. Everything inside here, sorry, it's hard for me to tell. Okay, here, sorry. This can be efficiently solved, right? So this is convex, this can be efficiently solved. Especially QPs can be solved really fast nowadays, right? Convex optimization problem can be can be solved instantaneously or in real time in general. But non-linear or non-convex problems are hard to solve in general. Okay, so so that's the categories, and we are going to discuss this part, this semi-definite SDP, in detail, maybe later today even in lecture 12. Which is a special convex optimization problems. Okay, the categorization of different optimization problems is only based on the properties of the objective function and the property of the constraint set. Okay, that's why we introduce set functions and also convexity, concavity. All right, so that's the categories. I think I need another page to discuss. Hold on. Okay, then how to solve optimization problems? Okay, although we don't write our own kind of optimization algorithms, how to solve numerically, how to solve optimization problems, how to find optimal solution, let's say that, sorry, how to find optimal solutions, sorry. How to find optimal solutions. If you have to find an optimal solution to an optimization problem, you first need to define or characterize what optimal solution is. Okay, it's like you want to find someone, you need to describe what that someone looks like, right? So that thing is called optimality condition. Optimality condition. basically characterize what optimizers need to satisfy. And that's the condition you use to find the optimizer. If you find me, you need to describe what I looks like. And that's exactly the optimality condition. And I think most of you, even from undergraduate calculus class, you have learned optimality conditions for at least some simple case. For example, for unconstrained problems. Okay. The optimality condition, let's say first order optimality condition tells us if X star is a local minimizer, let's say minimizer or maximizer, either way is fine. Let's say local, let's just say minimizer. It must satisfy first order necessary condition. It must satisfy. Then, Liu Ben, do you know the optimality condition? But then,
the gradient of fx star is 0.
Okay, why? Can you prove it? Can you prove it?
I could use the definition of the convexity.
Not convex. I didn't say convexity. This is not convex, right? It's arbitrary, unconstrained problems. Just nonlinear general, okay? General problem. Well, you can use Taylor expansion. Taylor expansion. You can roughly, I wouldn't call it proof. You can argue through that. So fx approximate equal to if you expand locally about this x star is gradient x star transpose, right? If you do this is a multi-variable functions, then x minus x star plus high order term. Okay, you can do second order expansion that will have Hessian going out. So this will be locally optimal. Well, if I want to define this very rigorously, well, we need to spend another slide or two to discuss what do I mean by local really optimizer. But let's assume you know roughly what it means, that locally around this x star, there's no other x that have a smaller cost. Okay, let me repeat, infinitesimally very close to x star, then x star is the best, it's the lowest cost, right? And if that's the case, then the gradient has to be 0. This is a 0 vector, right? Gradient is this guy is in Rn, right? It's defined as partial f, partial x1, all the way to partial f, partial xn. So this thing needs to be a 0 vector. If it's not 0, you can always pick some x. Okay, suppose this term is non-zero. Okay, and I can pick x1 a little bit below x star 1, so that I can pick other. Let me say that. Suppose partial f, partial x1 is non-zero. Let's say non-zero without loss of generality. Let's say bigger than 0. Then I can pick x equal to x somehow a non-zero hat. All those others are 0, where x hat, let's call that, sorry. Let me do this. I can pick this one to be x1 star minus epsilon. And all the other elements are 0. So if I do the inner product, that will give me I think it's a negative value, right? So this guy plus a negative value will be smaller So that contradicts the fact that X star is the minimizer. Okay, so roughly speaking, gradient has to be 0 in order for you to X star to be a local minimizer. Okay, I hope that's fine. But this only can tell you this is a local minimizer. So around this X star, this is the best. There's no other nearby kind of X that have a smaller cost. X star equal to 0 can also tells us this minimizer, maximizer as well. Okay, so we cannot tell. So important fact of convexity. So for convex problem, this condition, let's say condition 1, then condition 1 guarantees X star is global minimizer. Not only local, but it's also global, and it's also not possible to be maximizer. It's only possible to be minimizer. Okay, that's the important thing for a convex problem. We can think about this as a fact. You can also see that from the figure. Maybe that's a convex function, right? If satisfy this gradient equal to 0, it has to be a local and also global minimizer. All right, that's a quick summary of optimality condition for unconstrained problem. The question is, what about constraint optimization? Okay, so you can see that. So, well, if the unconstrained, you just need to find X star for which the gradient equal to 0. So optimality or optimization, because of this optimality condition, okay, enable you to transform the optimization problem to a nonlinear equation solver or root finding problem, right? You need to find a X satisfies certain nonlinear function of X equal to 0. You just not need to find the root of a equality equation. So that's typically how people solve it, right? Basically solve a nonlinear or linear equation. What about if this is constraint optimization? Then we need to incorporate the constraint, which somehow that's why we need to introduce the Lagrangian, basically trying to convert constraint problem into somehow unconstrained problem and state the optimality condition in the constraint optimization problem. Okay, that's I think some people know this Lagrangian. Let me formally define it. Okay, we have 4 minutes. Let's define this Lagrangian. Lagrangian is defined. First of all, you have an objective function, right? If you don't have any constraint, that's your Lagrangian, right? If I have constraint, you somehow need to incorporate that constraint in the Lagrangian, okay? So the way they incorporate them is first you add terms that relate to the inequality constraint, which is a lambda I times this is a fi, and this guy is and we require this one is called Lagrangian multiplier associated with this inequality constraint, and this is nu of I is the multiplier associated with the equality constraint. Okay, and we require, for example, let's say we require the multiplier related to inequality constraint has to be bigger than 0 for all I. Okay, so if X is let's say if X is a feasible solution, means it satisfies all the constraints, then this term will be 0. Okay, if it's non-feasible, then this term is non-zero. Okay, and this term is interesting. If this satisfied constraint because we require the lambda I multiplier to be positive, we know fi of x has to be less than or equal to 0 for feasible x. Then this term eventually will decrease the cost, okay, overall Lagrangian value. Right. So this is defined as the Lagrangian. The way we define it, we can somehow transform this into we can state the optimality condition in a convenient way. Right. Before doing that, let me define another important definition, which is dual function. Okay, the dual function is defined as we minimize over x of the Lagrangian function. So we can, based on the definition, I'm not sure whether you can see that. So this is basically inf means, for this class, you can think about inf means minimize. Okay, but it's mathematically different. But you can think this way. You can think about the minimize over x, all the possible value of x of the Lagrangian multiplier for Lagrangian for its given multiplier. So this is a function. Dual function is a function of the multipliers. Okay, multipliers. Okay, which is lambda and nu. Okay, and so the way we define this function for each lambda, each nu, we define this as the minimum value of Lagrangian over all the possible x. Okay. So if we write it down, it's like this. And I want to finish before taking the break. I want to discuss this. So G is a concave function. Okay, concave function for, okay, let's say from concave function. This is always, right? Let me put that, this is always true. Okay, so no matter whether the original problem is concave, or sorry, is convex or not, the Lagrangian dual function defined this way is always a concave function. It's always true, regardless of whether the primal problem is convex or not. What do I mean by primal? Is I refer to this, let me call it primal problem. This problem is a general nonlinear non-convex problem in general. Okay, it could be convex, could be affine, could be linear program, could be QP. Okay, could be non-convex. Right. So whatever this problem is, the dual function is a concave function. Okay, so I want to briefly discuss that. This is a because let me say that. So if x lambda nu is affine in lambda and nu. Okay, that's the first fact. Because the way we define this function, look at this. It's a affine function of lambda and nu for each x. If you fix x, this becomes a function of lambda and nu, and this function is affine. I think that's clear from this expression. And second, the pointwise minimum mean of affine, which is affine. We can think about this as a concave, right? Affine is concave, is concave. That's a property we just discussed before, right? So if you do a pointwise minimum of a bunch of a concave function, it gives you a concave function. So no matter what the original, what's the structure of f and h in terms of lambda and nu is always a concave function, this dual function. Right, that's a very important property. Okay, I will take a break and then come back to discuss the other properties. Okay, so now we finished the defining the dual function, and actually, a dual function have very important properties. The first property is always concave. That's the first property. And the second property is always gives you a lower bound of the primal optimal solution, optimal cost. This P star is the, I think we defined it as optimal value. That means when you minimize the minimum cost function value you can obtain, it's P star. Okay. So it's always give you a lower bound for any feasible lambda. It gives a lower bound of this P star. We can prove this by this is quite simple to prove, but it's important to illustrate this some kind of subtle concepts. So let me go over the proof. So let's say I have a let's call it x tilde. Let's be arbitrary. Primal feasible. Okay, this is a feasible primal variable. Okay, and assume lambda is bigger or equal to 0. So I use this kind of curly type of inequality. That means this means I said this means element wise. That means lambda is it has a m-dimensional vector. Okay, so that means lambda 1 bigger or equal to 0, lambda 2 bigger or equal to 0, element wise lambda m bigger or equal to 0. Okay, so it's all the elements is bigger than 0, and primal feasible. What I mean by this is, as I mentioned before, that means it satisfies this x tilde satisfies if I tilde less than or equal to 0, satisfies inequality constraint, and also satisfies the equality tilde equal to 0 constraint. All right. So suppose that's a feasible solution, then I can say the cost of this guy is always bigger or equal to L x tilde lambda and nu. I'm not sure whether you can see that. If x tilde is feasible, that means satisfied is constraint, then this term is 0. Okay, and this term always is negative in this case because lambda is positive. This guy is negative or 0, right? It's no bigger than 0. So I've plus that will be giving a smaller value. So this will be bigger or equal to this Lagrangian. Okay, and this guy of course equal to bigger or equal to the mean, or if I use inf, the inf of x over x lambda nu. Okay, so these two are fixed values for arbitrary, right? And as long as lambda is let's fix them. Okay, let's fix arbitrary lambda bigger or equal to 0, and nu is arbitrary variable. Then if I do this function is always bigger or equal to the inf, because inf is over all the possible x. You pick the smallest one, which give you the smallest L value, and a particular x will be bigger than that, right? And this guy, by definition, is g of lambda nu. Okay, and because for arbitrary feasible values, this cost function is bigger or equal to this particular dual function, then we can say if I take a mean over x tilde feasible, and I have 0 of x tilde is also bigger or equal to that. Okay, so you can think about this. Let's fix lambda and nu first, and lambda need to be element-wise positive or non-negative. Then we can define Lagrangian, and we can view our Lagrangian as a function of x tilde. Okay, we only you can think about this, the left-hand side has a bunch of function values that are all bigger or equal to that. Okay, the mean of that bunch of functions will also bigger than the right-hand side. That's where this is this holds. So this guy is my primal. Okay, so if you already derived the dual function, then plug in any kind of dual feasible, which is lambda bigger or equal to 0, will give you a lower bound of the primal optimal solution. Okay, the dual function, you can think about picturely, always stay below the primal function. Okay, so then we can define the dual problem, which is maximized. So dual is always stay below the primal. Okay, you can think about this. If this is a convex problem, this will be my fx. This is maybe f0x, and dual is always concave. It's like this. Okay, they are defining different variables anyway. So so in this case, dual is always stay below the primal, and we can try to maximize the Lagrangian dual problem. Is just try to maximize the dual function subject to the dual feasible variables, which is only about lambda. Okay, the inequality related multipliers. You can think this as finding the best lower bound of P star using the Lagrangian dual function, because each of this is less than P star. You want to minimize or maximize this lower bound. Eventually, hope you reach that the P star. That will be called the zero duality gap, right? So this problem is equivalent to, if you think about it, maximize. If you transform to the standard optimization problem, that will become minimize negative G lambda nu, okay, and subject to negative lambda less than or equal to 0. Because why we do this negative? Because we want to transform into the standard form, which is minimize and subject to inequality constraints that are a function of less than or equal to 0. So because of this, it's a concave. G is concave, so negative G is convex, right? It's a convex function, and the variables are inequality constraints are linear even. Okay, so this is a convex optimization problem. Okay, the dual problem is always convex. Okay, this is always under no additional condition, right? I don't need to assume the primal to be convex. The dual problem is always a convex optimization problem. Okay, regardless of whether the primal is convex or not. So sometimes it's easier to solve the dual problem and then come back to solve the original one. Okay, so this is always a convex optimization problem. Yes, even when the primal is non-convex, the dual problem, let's say the dual problem is a convex optimization problem even when the primal is non-convex. Okay. So the optimal value is, let's call it D star. So that means if you maximize this, you somehow try to find the largest G value, which let's call that D star. And this you optimize, let's say this part is optimized variable is lambda nu, is a function of lambda nu, and nu has no constraints. Okay, let's say nu belong to our, I think I called it Q, right? We have Q equality constraints. Nu has a Q dimension. So lambda and nu is called dual feasible if lambda, the lambda part is bigger or equal to 0. All right, that's our requirement. And sometimes also simplify by making the implicit constraint on this belong to the domain of G explicit. I think that's a little bit abstract. Let me jump over to an example so that you have a more concrete feeling about what this means. Again, this theory doesn't indicate anything about how you numerically solve the problem. It's just you need to know the duality, the dual definitions, and that gives us Kkd conditions and the duality theorems. Okay, let's look at a very classical problem with a linear program and try to find its dual. Right. So this is a linear program because it optimizes a linear function of x, this over x, and subject to equality constraint and the linear and also inequality constraint. That's a standard form of linear program, which is written in this way. Okay, so that means x1 bigger or equal to 0 all the way to xn bigger or equal to 0. So the inequality constraint is only related to x. Okay. So all the linear program can be written in this way. Let's look at this particular. Let's define the Lagrangian function. Okay, so let me ask someone to write this for me. Maybe Zhu Xiyu.
First, I think is say transpose x
Right.
plus lambda and x. I think is ix, which means x over.
Okay, so let's lambda I. You mean?
Yeah. Times ix. Which
summation. Okay.
Yeah.
Okay, and anything else?
Plus we
nu. Let's call the nu. Okay, nu I. Let me finish this. Okay, q times ax minus bi. But let's using a vector form, which is this is a vector. Okay, so nu transpose times this. Are you fine with this? And this term, I think we're missing one thing. This is the negative xi. Because the standard form, we need to have fx less than or equal to 0, right? So here is bigger than 0, so I need to have a negative sign. Are you with me?
Yeah.
Okay, so this is less than or equal to 0, so that's negative x. If in vector form, I will have, let me directly write down the vector form, which is lambda transpose times negative x. That would element-wise lambda I plus times xi. Okay. Okay, good, great. So that's the Lagrangian definition. Then I can define the dual function lambda and nu. By definition, that will be inf over x in Rn in this case. The definition, right, of this function. If I group terms a little bit, there's something related to x, which is, let's call that C transpose minus lambda transpose. This term is plus nu transpose A, right, times x. There's also a kind of scalar, sorry, this is a constant term which does not depend on x, which is negative, which is negative nu transpose B. Okay. Okay, I'm directly copied the definition. I haven't solved it yet. So you can see that in terms of defining the dual function, you somehow need to solve an optimization problem already. Okay, so for many problems, it's really hard to derive the dual function analytically. Okay, but in this case, we can. I'm not sure. Maybe Zhu Xi, we can continue. What do you think the solution should be? You want to minimize over x and about this number. Okay, what do you think the solution will be?
Okay, I should think.
Let's say if you minimize something like a 2x plus 3 over x, let's say in scalar case, what do you think the solution will be?
Yeah. First, I should to determine the sign of the first brackets.
Okay.
Yeah.
All right.
If it's positive, so well, I should to calculate in the minimum of the domain.
Okay, but it's in Rn, right?
Okay. Yeah.
So it will be negative infinity.
Yeah.
Okay.
Okay.
So if but the condition is if C transpose lambda nu A not equal to 0. Okay. So if this term is non-zero, you can always pick X such that the cost can be arbitrarily small, arbitrarily negative. All right. I'm not sure whether you can see that. For example, if I want to minimize over this function in R, then it's negative infinity. I can pick negative 100, negative 1,000, negative 10,000 to there's no kind of limit. I can decrease the cost forever. So that would be, even though I can say this is a negative 2, it doesn't matter. I can also pick a positive 100, positive 10,000, positive thing to decrease the cost. So as long as this coefficient is non-zero, because I minimize over the entire Rn, so this guy will be negative infinity. The only case it has a finite value is what? It's if C transpose lambda plus nu transpose A equal to 0, then the value will be just this, okay? Just negative V transpose B, I can also write a B transpose nu. All right, so that's my that's the function. So some part of the function is negative infinity, and some part is it has a value, and okay. So now we need to maximize. So for the dual problem, let's say for the dual problem, we need to maximize over feasible lambda. Okay, let's say optimize lambda. Lambda has to be bigger or equal to 0. That's my definition. So G of lambda nu and subject to let's say just sorry. Let's just say lambda and nu subject to lambda bigger or equal to 0 for each element. And also I need to, typically we can call this part if lambda and nu satisfy this, means this is a dual feasible, or this is belong to the domain of G, for which G is not infinity or negative infinity. So, but you can see that we only need to optimize over which the equality holds, because otherwise the sign is always negative. Negative infinity. So this will be what? It will be C transpose minus lambda transpose. Do I have transpose? Oh, sorry, I have a transpose here, right? Right. Lambda transpose plus nu transpose A equal to 0. Okay, that will be my formulation of the dual problem, dual optimization problem. It's clearly a if you do this case, that will be my this will be my cost function subject to these constraints, right? And I'm not sure whether you can see that these two constraints together tells you that. So it will be maximized. You substitute this. The only case you have this value is because of you have to satisfy this equality constraint. And these two things together, because of lambda has to be bigger or equal to 0, and lambda nu need to jointly satisfy this equality constraint. So I will have these inequalities, right? That's basically you move lambda to the right, then this thing has to be bigger or equal to 0. Okay, I eliminate the equality constraint and express this inequality constraint in terms of nu, right? So that will become my dual problem. Okay, so sometimes the dual is easier to solve, sometimes the primal is easier to solve. For example, this guy has the the primal problem has let's say n variables. This is n. This axis belongs to Rn, so it's n variables. And let's call that M equality constraint. Let's see. Yes, M equality. Let's Q equality constraint. That's typically I call it Q equality constraint. And N inequality. Okay, that's my decision variables. And the other one is I have, I think I have Q variables. This is only new, right? The Q variables, decision variables, and also N inequality constraint only, okay? Okay, but numerically we don't do this back and forth. This is, I think, mostly, at least to me, okay, mostly primarily for conceptual understanding of optimality conditions, right? I hope that's give you a example about how to define Lagrangian, how to derive dual functions, and you can see that it's non-trivial to find the dual function, and you need to solve optimization problem. In this case, you can do that analytically, and you're in the homework. I will ask you to derive dual for SDP problem, but it will be harder. But anyway, it's typically harder, or sorry, not easy to find. But in this case, we can find it, right? And we have derived the dual problem. Okay, that's the this part. Let's move back to our discussion. Okay. Then it's for us to know important theorem, which is called duality theorems. As I mentioned before, all the dual function for each dual variable gives you a lower bound of this guy. And so if I have solved the dual problem, the dual optimal cost will always give us a lower bound of the primal. Okay, this is always holds, no matter it's convex or non-convex. Okay. And this can be used to find non-trivial lower bounds for difficult problems. Sometimes it's hard for you to find the exactly optimal solution. Okay, and but you can use dual problem to find a lower bound. Let's say you say you want to minimize some function. The lower bound is 10. Okay, and you mean the optimal function cannot be lower than 10. Okay, but you already randomly find some kind of solution which give you a cost which is 11. So you are confident enough to say, okay, at most the error will be 1, right? So that sometimes give you a nice way to quantify the performance of a solution, which you don't know whether it's optimal or not, but at least you know it's not too far from optimal. Okay, so that's roughly. I think you can hopefully you can see roughly what I mean. And the strong duality is so-called duality theorem, strong duality theorem, which is sometimes the dual solution is the optimal solution. Sorry, the dual optimal cost is equal to the primal optimal cost, with D star equal to P star. This is not true in general. Okay, this one is always hold. Okay, always can be used to find the lower bound of the optimal cost, but the strong duality only holds in kind of special case, but fairly general case. Not true in general, but typically holds for convex problems. So if the convex optimization problem, an important theorem is strong duality. The dual optimal gives the primal optimal. They coincide. It's also called there's no duality gap. Conditions that guarantee strong duality in convex problems are called constraint qualifications. Typically, we don't dive into that details. You can somehow, if you use it, you can assume most of the time it holds. All right. If you want it really picky, and you need to check the constraint qualification, and one particular constraint qualification is called Slater quantification. Sometimes you may see that from the literature, and it's very easy to check. It's just primal is strictly feasible. Okay, but strictly feasible is that, i.e., there exists a particular point, not only feasible but also strictly feasible is that the fi x tilde not only less than equal to 0 is less than 0. Okay, and also the inequality, the equality part it also holds. Okay, so if that satisfies this, then the primal strictly feasible, then the strong duality holds if the problem is convex, right? All right. The main reason I think for introducing this Lagrangian is really to state or generalize the unconstrained optimality conditions to constraint problem, how to state the optimality condition. Okay, there's I think if you took class in optimization or other class of optimization, if you read books, they will have many different variations of these optimality conditions. Okay, even Kkd condition, there's many ways to state them. So I just list, I think the most general, at least to me, the very kind of easy to remember and the most general conditions. So I don't need to memorize a lot of subtle conditions, assumptions. Sometimes they require the constraints are independent, things like that. Okay, so let's not worry about that technical details. In terms of optimality condition, general optimality condition, we can state it into this 4 requirement. Okay, the first one is called Lagrangian optimality. That's my term. Okay, so so anyway, so the primal. So let me state the theorem. Sorry. So suppose general optimality condition. Okay, so this problem, given this problem, we can define the Lagrangian. All right. So x star lambda star nu star is primal dual optimal, means x star solves primal optimism problem, and the lambda star nu star solves the dual optimal optimism problems. If and only if, okay, if and only if this x star lambda star nu star satisfy these 4 conditions. Okay, so if this is primal dual optimal and also strong duality holds, suppose these 2 are the conditions that we care about. If and only if these 4 conditions holds. Okay, Lagrangian optimality, complementarity, primal feasibility, and dual feasibility. Okay, these 2 are pretty easy to understand. If this guy solves the primal problem, there has to be a feasible one, right? That's only state the feasibility. And if lambda nu solves the dual optimal, it has to be the dual feasible variables, which means the dual kind of constraint only require the multipliers associated with the inequality constraint has to be bigger or equal to 0. Okay, these 2 are pretty simple, right? And also this guy has to hold. So given these multipliers, lambda star has to be the optimal or minimizer of the Lagrangian. Okay, I didn't say this is convex or not yet. Let me repeat that again. I don't care whether this problem is convex or non-convex. Okay, I just need to satisfy these 4 conditions. That means this guy is primal dual optimal solution. And one special case, one condition is that x star has to minimize the Lagrangian for the given dual optimal solution, right? And also complementarity condition is that the multipliers associated with with the inequality constraint have to satisfy this complementarity condition. Okay, that means multiplier times this has to be 0. So that gives us 2 cases, right? Because lambda I is 0, then fi x star arbitrary. That's first. The second case, hold on, lambda I, sorry, this is 0, this is arbitrary, can be bigger than 0, right? Then if star has to be 0. Okay, that's called complementarity condition. We can prove it, by the way. Let's try to prove this most general optimality condition. It's fairly, I wouldn't say easy, but if you recognize the nature of the problem, something becomes less technical, so it's a little bit easier to get. Okay, let's prove the necessity. Means that suppose this primal optimal solution with zero duality gap, that's the assumption. Then let's assume that let's derive those 4 conditions has to hold. As I mentioned before, the last 2 are pretty easy to do and pretty clear from even the definition of the optimality optimal solution. And the first 2 are something we need to spend some effort. Okay, but it's also very simple. So for example, this guy is the primal cost, right? And because we say we assume zero duality gap, that means the primal, this is a P star, equal to D star. That's our assumption. Suppose zero duality gap. Okay, let me emphasize again. Zero duality gap just by definition means D star equal to P star. It doesn't need to be convex. It's for whatever problem I can define primal and dual. Okay, dual is always convex optimization problem. Primal may not. Okay, and the zero duality gap has nothing to do with whether the primal is convex optimization problem or not. It's only required the primal optimal cost equal to the dual optimal, right? P star equal to D star. And if the convex problem satisfies constraint qualification, then zero duality gap always hold, right? But when we state these general optimality conditions, we assume strong duality, and this is the primal dual optimal is equivalent to these 4 conditions. Okay. So let's assume zero duality gap. That's our assumption. And okay, in this case, we can just write down the definition of the dual function. Okay, the dual function is minimized over the Lagrangian over all the possible x. So in this case, this function will be our L, x, lambda star, and nu star. Okay, I'll optimize over that. That will be definition. This is the definition, by the way, almost. I changed my inf to this min here, okay. So I would say this guy is minimized always less than equal to f0 x star plus this. Liuben, do you know why?
Because this is a point-wise minimum function.
Okay. If I write it in a more compact way, so that means min over x lambda star nu star is always less than equal to L x star lambda star nu star. Do you agree this?
Yeah.
Of course, the min over x is definitely less than a particular x, right? This is a particular x star. The other side is I take the min, right? That's the definition of min. It has to be less than any x, in particular I pick x star here. Okay, that's the least step. That will be my least step. I hope that's fine. And because I know it's primal dual optimal solution, that means it satisfies the constraint, right? So this means satisfy the constraint. So when satisfy the constraint, this guy has to be what? This guy, if satisfy, I know lambda 0 bigger equal to 0 by dual feasibility. Okay, and I also know lambda x star, f star less than or equal to 0. This is primal feasible, right? This is a primal feasible. You x star, if a plugin has to satisfy the constraint, otherwise it won't be optimal solution. So because of these two, this guy has to be less than 0, less than or equal to 0. And this guy is always 0 because of x star is feasible, means h of x star has to be 0, equality condition. So overall, this is less than 0, this is 0. So overall, it's less than or equal to f0 star. So I hope that's fine. Now you see a kind of interesting inequality. So you start with f0 x star. Eventually, you figure out, okay, all these inequalities equal or less than equal to that, right? You know this guy is just this, right? So overall, all these inequalities has to be equality in order for this thing to hold. So there's no gap in each of these inequalities. Otherwise, you won't reach the a less than or equal to a, right? So in between whatever the inequality introduced, it has to be equality, all right? So therefore, all inequalities are exactly equalities. So I can change this guy to equal to this guy equal to, all right? So replacing the first equality, I can get what? So if this inequality, I know now it should be an equality sign, then that means the x star is the argument. That gives us the Lagrangian optimality first condition, and the second is that if I do this guy, the second inequality, then I know complementarity condition. So I derive it without assuming complementarity condition. I derive it only because these are primordial feasible. So I have an inequality sign here instead of an equality. But because of we start by assuming the zero duality gap, we somehow know all the inequalities should be equality. Then I know this guy is equality, then that means this guy has to be 0. Because if this is equality, we know this is 0 already, so this has to be 0. That gives us a complementarity condition. Okay, there's many ways to prove different variations of this optimality conditions. I think this is a most it's pretty high level, but tells you the importance. So okay, let me repeat. Okay, so we derive that if strong duality holds and we know this guy is primordial, then has to satisfy these 4 conditions. So that's what we have done. That's called necessity. And the other way around. So if this guy satisfies the optimality condition, then it must be the duality, zero duality gap, and also this pair has to are the primordial optimal. That's the sufficiency. That's also easy to find. Suppose we satisfy these 4 conditions, then this guy, which is let's see, satisfy the optimality condition, then we have let's see, this G of lambda star nu star equals to this. This because of what? This because of the complementarity condition, right? Did I say that? Our first equality is Lagrangian optimality. Okay, yes. Well, okay. So this guy is, I think, this guy by definition is mean over x, right? Have x lambda star nu star. Okay, and which is a Lagrangian optimality condition. X star is the optimizer of this, so I can plug in this guy. Yes. Okay. This is because of a Lagrange optimality. I can have the first equality sign. The second equality is due to complementarity condition because this guy is 0, and this guy is also 0 because this is a primal feasibility. This is 0 because primal feasible. Okay, I hope that's fine. Okay, so this guy equal to this, and this is the primal feasible, and this one will be my optimality. This will be my P star. This is my D star. Okay, so anyway, this will be my dual equal to this, and primal solves the. So this pair solves is the primal dual optimal solution. Okay, I skip a few lines of things since I want to finish the examples. Okay, anyway, I want to quickly go over the Kkd condition that people often see. I think my computer is slow. From other textbook, which is, I guess, is this one. Okay, so for convex problems, you have a Kkd conditions, right? But this Kkd condition is just a special case of our general optimality condition. Let me repeat. You just need to remember the general optimality condition. Then we can derive the Kkd conditions based on additional assumptions of convexity. Okay, you just need to replace. I think these are all the last three conditions are the same. You just need to replace the Lagrangian optimality with a first order optimality condition, right? Because of due to primal convexity. So primal problem is convex. So the primal optimal, you need to find the global optimal solution of the Lagrangian, right? So that's the first order condition gives you that. Okay. Let me repeat. This ensures the Lagrangian optimality condition if the problem is convex, the primal is convex. Okay. So I think I just need to mention this part, and these are also more general than many, I think, conditions I see from other textbooks. But I think it's important to see the nature of the conditions instead of looking at the special case, state the conditions in a very, very detailed way, right? I think all of you need to remember this guy, and also need to go over the proofs, especially this part of the proof. I think this is also important, but I may leave a homework because I leave one step I didn't discuss. I will skip the linear program already. I will skip the quadratic part. Let me just directly have 5 minutes. Let's look at the Drake examples. As I mentioned before, the reason we want to introduce optimization is just want to make sure you can use it, right? Drake is kind of not only for robotic simulation, but also it's a very powerful tool to solve optimization problem, design controllers. So this optimization kind of functionality is very kind of very good. And let's work with an example. Suppose this is also, Ruben, what is this problem? This is what kind of problem?
This is linear programming.
Okay, it's a linear program. What I want is, hold on, I think I'll minimize. Okay, I want to minimize 5x1 plus 6x2 subject to that, okay? And for Drake, I will upload the code later on. I'll be quick, okay? So you need to define a mathematical program, then you define variable. In this case, I define x. And after this, I think Drake has the internal kind of symbolic expression. If you say 2 times x, if you print, I think, let me check that. This expression, right? For example, you can say x 0 times 2. It's just an expression. You can just use that as a symbol, right? Let me do this here. So if I want to do this, I can first add cost. The way we add cost, I think there's a tutorial. You can follow that. I have a little bit more than the tutorial, so it's better for us to do this. So it's a program. I call it program. Add cost. Okay, you can do that. Add cost, right? And what kind of cost we want? It's 5 times x1, which is well, here is the index start from 0, so 5 times x0 plus 6 times x1. Okay, that's my cost. I can call this cost. Okay, equal to that. Okay, that's already at a cost function that defines our cost function. And we can also add constraint. How many constraints I have? I have 3 of them. And the tutorial also mentioned a way to add them one by one. Let's say, I'll just say program dot add constraint, which is x0 plus x1 equal to 10, right? Less than equal to 10. So less than equal to 10. I think that should work. Yes. And you can add this kind of cost, which is x0 minus that bigger or equal to 3. Bigger or equal to 3. And the same thing is that 5 times x0 plus 4 times x1 less than equal to 35. Okay, that's my problem. And then later we can solve it. Okay, we can solve. Let me put this guy here. The optimal value is a linear program. The optimal value is just 0, -3, 10. Okay, you just need to tell the trick what your cost and what your constraint. That's it. And this is a little bit cumbersome if you want to have a large number of constraints. So it's important for us to know how to do that symbolically and from matrix form. In this case, I can define C as my, let's see, C is my an NumPy array. That's NumPy array. Let's call that, because this is a linear, right? This linear is a 5, 6 inner product with the x vector. So I will call that 5, 6. Okay. Then I can also say this is cost equal to prod add cost, which is C. Let's add x. I think that should be okay. Okay, it doesn't work this way. NumPy array. Let's see it out. Let me think. Q dot transpose. Okay, maybe C dot transpose add x. Cost program add cost. Input operator mismatch dimension with 0. What's my dimension? Sorry. 啊？你说？啊？哦 ，OK， 我写的错了。OK， this is 2. Yes. Okay. I think this will work. Okay, that's good. What else? Then I can define the constraint like A. I'm not sure whether you can see that directly. Okay, this is a 1, 1, 1, -1, 5, and 4. Okay, that's my A matrix if I want to do matrix. So numpy dot let's say mat. So it's 1 1. What is it again? 1 -1 and 5 and 4, right? It should be okay. So that's how many constraints? How many constraints? I have 3 rows. That's 3 constraints, 2 variables. So that's A, and B is something I want to be less than or equal to. Hold on. So this will be okay. This is smaller than or equal to 0, 10. I should change the sign. Sorry. This guy is -1 and 1. And the other one is negative, less than or equal to 0. Okay, so B is B should be numpy dot array. What is it? It should be the first one is what? All right, 10, -3, and 35. 10, -3, and 35. Okay, and then I can say add. Let's say let me return constraint equal to plot that dot add constraint, and LE is less than equal, but in a symbolic way. So it's A at X B. Not sure whether that works or not. Okay, that works. That means A times X less than equal to B element each row. Okay. So overall, I have cost, I have constraints. I can say, let's say, I will copy this part then. 0 and -3, 0 and -3. Okay, we did exactly the same formulation, but it's more compact. Okay, so you need to use the symbolic less than equal things. And I will add another example with the quadratic program, also in the matrix symbolic way, so that you can see how this can be done, so that you can do some homeworks on this. Okay. Eventually, next lecture, I think 2 lectures from today, will be talking about differential IK that you need to solve QP using Drake to design motion controller for robotic arms. Okay, that's all for today.